Hi, I'm Ben-Yaakov. This presentation is entitled Addendum to Ripple Cancellation in PWM DAC, Digital Analog Converter, or subtitle, There is More Than Meets the Eye, or Never Too Late to Learn Something New. So this presentation is related to a previous video that I have posted in my YouTube channel. This is the link. I'm going to put the link also at the page of this video, the YouTube. And the previous video was about ripple cancellation of PWM signal that you want to convert it to DC or to an analog signal, and this is done by putting a filter. But in order to reduce the ripple of the filter, there's a way to put an inverter and then another branch, so that you are actually generating here an AC signal which is in the reverse polarity of the original signal. And by that you can cancel the ripple, partially cancel the ripple of the RC filter. And I've shown that this is pretty nice. Again, the idea here is the PWM, original PWM. This is an inverted PWM, and because there is a capacitor here, we don't have the DC component, we have only the AC component. So we have an AC component coming from here, generating a ripple here, and then we have an AC component which is in opposite polarity, and therefore the ripple will be cancelled out. So this looks pretty good. But as a matter of fact, as noted by one of the viewers of the previous video, he wrote to me and he said the following. He tried the idea of ripple cancellation and compared it to just a filter with two sections. That is a two-pole filter, RC filter, in tandem, two RC in tandem. That is second order, but RC filter. And what he says, that he got the same result, just about the same ripple. That is, the idea of the ripple cancellation is very nice, but using an RC filter, two-pole, gives you the same result. Well, let's have a look at it. I'm now going to compare the performance of this ripple cancellation idea to the performance of this filter. And here it is. This is a schematics, a PSpice schematics I've shown in the earlier video. This is for the ripple cancellation. We have here this is generating PWM, and then this PWM is then fed to the RC filter, and then we have an inverted PWM which goes in here and it comes out. And so this is the output for this ripple cancellation. And then I've taken the PWM and also passing it through a simple two-pole RC filter. Okay, and this was done for 30 kilohertz PWM signal. Note that this is a parameter, this capacitor that I'm varying. The output here of C2 is 10 nanofarad, and here is a two-pole filter. So here are the results for C equal to C2, that is, this C equal to C2, compared to this. And as you can see here, the green one is the ripple cancellation, while the red one is the 2RC. In fact, the 2RC is a little bit better. The rise time is about the same, and the ripple is in fact larger in the ripple cancellation scheme. So now I've changed C to twice the value of C2, that is, this one is twice the value of this. And what I see is the following. The ripple is the same as the ripple of the ripple cancellation method. The green one is the same as the two-pole case, but the rise time now is corrupted. That is, the two-pole in fact has a better rise time than the ripple cancellation for the same ripple. So not only that the ripple cancellation is about the same as the two-pole simple RC filter seems to be a little bit better. So why is this? Well, we can understand it by doing, say, a superposition of the signals here. So what I'm doing here, I'm first of all looking at this path. So I see R1, and this should be C1, C1. And then these two are in parallel to the C1 because this is low impedance. And then I'm looking at this path, and I see R2, C2, and then I see these two in parallel. Now, ideally, you'd like C2 to be very large, because otherwise, if C2 is small, or the capacitance is small capacitance, then the signal here will not be exactly inverted. It'll be distorted, and also you'll have a long rise time or setup time. So you like C2 to be very large. In fact, you like it to be infinitely large. But C2 is here, in fact, in parallel to C1. It's parallel to here. So therefore, once you make C2 large, in order to get a better ripple cancellation, you actually move the breakpoint, the quarter frequency of the original filter, to a lower frequency. Obviously, the ripple will be better, smaller, but the bandwidth will be smaller, and therefore the rise time will not be as good as with a smaller C2. So there is a compromise here, and whatever you look at it, you end up with the fact that this circuit and the double pole RC circuit are about the same. And so this ripple cancellation is a neat idea, but it's really not adding much. So what can be done? Well, there are solutions. There is, in fact, an IC made by Analog Devices, LTC2645, and it is a 4-channel unit, and it includes, first of all, a sort of a counter here, which is measuring, in fact, the length of the pulse as compared to the period of the PWM, generating a binary number and putting it into a DAC and getting an analog signal. And there are 4 channels like this. This is kind of too heavy because we wanted to get away from the digital to analog converter, and here we get it at the back door again. Now, obviously, there is an advantage of using PWM as compared to running an analog signal, because the noise immunity is better here. But at the same time, you do have a DAC, a digital to analog converter, with a serial input. Needs only one line. So in fact, you can get one line from a port and then feed it to a DAC, and that's it. You don't need the whole thing. So this is one solution. There are other solutions that have been described in the literature, and here is my version of it. All the solutions are pretty much the same. This is just a way that I look at it, and this is the following. We can generate an analog signal which is proportional to the duty cycle, that's what we want, or the width here, by doing the following. First, we have an integrator which is fed by a constant current, and this is of course a constant capacitor. So we have a ramp here. We start the ramp at the beginning of the pulse, and then we sample it at the end of the pulse. So this is in fact a time to voltage converter, because the time will determine the height here, and that's what we want. Once we get this value, we sample it and put it, sample and hold, on this capacitor. So in order to do it, you need a current source, you need a capacitor, and then you need a means to reset the capacitor to discharge it at the beginning of each pulse. So this leading edge here is used to reset the capacitor, to discharge it. And then the trailing edge here is used in order to sample the value here. Okay, so this is used here to this one here. It's an inverted. This is the PWM, so you have to invert it in order to get here positive value. So this is why I have this PWM hat here to get the positive pulse at the end of the pulse. So let's see how does this work. Before that, let me show you how I simulated it. This is an LT Spice embodiment. I have here a comparator which is comparing a triangular wave with either a step or a sinusoidal waveform to generate PWM. So this is the PWM line. And then I have two switches. One is getting the PWM signal as it is. Here it is. And this is for shorting. This is shorting. And here I'm sampling the ramp. This is just a buffer. This is a buffer, and this is a buffer so as to not to load this point. And then I have here an inverted PWM signal in order to get the trailing edge positive for the sampling. And then I compare it to a simple RC and a two-section RC. Okay, so it's 1 and 2 section, and the whole thing here is running at 100 kilohertz. So let's see what we get here. So this is the original signal. This is for a square wave, original signal. This is the sample and hold output. Very, very nice. These are flat completely. This is the single RC, fairly high ripple, and this is the double RC, two-pole. You see that the ripple, of course, is much lower, but then, of course, the rise time is corrupted, okay? So here is a zoomed view. Here we have the step, original step. This is the sample and hold. You see here one step here, and this has to do with the ratio between this capacitor and the sampling capacitor. If this would have been much smaller, this C3, much smaller than the integrating capacitor, then probably we wouldn't have seen the step. But here we have one step, so within one step it's getting to the new value. It's very nice, very clean here. This is an RC. We see the ripple, and this is the two RCs. Again, the ripple is much lower, but of course the rise time is much longer. So we trade the ripple with the bandwidth. And here we have a sinusoidal waveform passing through the unit. This is the original signal. This is the sample and hold. This is the RC, and this is the 2RC. This one is has a little bit of a ripple, of course, much lower than the single RC, a little bit more than we can see than the sample and hold signal. This is 100 hertz. The PWM is 100 kilohertz. Now we go to 1 kilohertz, the original signal, sample and hold. This is the RC. This is the 2RC. We see again a little bit of a ripple. Amplitude is okay, so we are in good shape here. Now we move to 10 kilohertz. This is 1/10 of the PWM signal. Here we see very nicely the sampling. See that we sample, and obviously this is now the PWM time. There's nothing you can do about it. Of course, with some processing, you could have smoothed this thing, but this would require, this is just a 10 microsecond period. So this is, again, the original, the sample and hold. This is the 1RC, and here we see the 2RC. Now, this is, of course, cleaner, again, because of the two sections, but already here we have quite a bit of attenuation, because the original signal is 3 volt here to the peak, and here we get already attenuated signal. So the bandwidth of this RC2 is smaller, and of course the smaller the bandwidth, you get lower ripple. And finally I'm getting here to 30 kilohertz. This is pushing it too close to the PWM frequency. If it would have been a step, then it would have been straight line. But as this thing is changing here, we have only 3 points, so 3.3 points per cycle. So it's a very bad sampling here. This is why we get this jagged waveform. And then we have here, also we see some delay in the sampling here. And here we have the RC, single RC, which is not so bad, but the ripple, of course, is very high as compared to the signal itself. And the 2RC is much better, of course, but again, it's already quite a bit attenuated. That's a lot of attenuation here because the bandwidth here is lower. So what's the conclusion here? Well, there are many ways to go, and you can do it in a simple way. You can do it by ripple cancellation. You can do it by sample and hold. It would appear, though, that simple filters, first order, second order, maybe a more sophisticated filter, like one with a inductor, so it'll be with a complex 2 second order transfer function, could be actually better. You can also use, of course, an active filter to mimic any order that you want and get, of course, the thing cleaned up. Again, if you use a higher order, you may have a problem with the rise time and with the phase. I haven't shown the phase here. There's an issue with the phase. So this is the conclusion that I can draw from all these examples that I've shown. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it'll be useful to you in the future. Thank you very much.